Hi everyone. So let me welcome you to our POP webinar on OpenMP 6. This is part 1, and today we are going to cover new features with particular focus on the host-side programming. That means traditional CPU programming. My name is Christian Terboven from RWTH Aachen University, and the co-speaker or co-presenter is Michael Klemm from the OpenMP Architecture Review Board and IMD. And we will tell you about 1 minute about our background in a second, but let's first take a look at the agenda. So we start with an overview about how OpenMP is coming together. Yeah, let me call that the OpenMP development process. And Michael is very well qualified to explain that because he's the CEO of the OpenMP Architecture Review Board. That's the organization that owns the OpenMP specification, namely the standard. And then he will continue talking about improvements regarding the base languages in OpenMP. That means C, C++, and FORTRAN. And yes, you can really ask him FORTRAN questions, tough ones, at the very end. Yeah, so he will have an answer on you. Then we switch topics. First, talk about what's new in tasking. There, you might have heard about it, a couple of really new features. Then again, Michael on loop transformations. And the final section is called some other features. It's only one other feature because we have to fit it into the time, which will be inductions. And then we are there to answer any question that you might have. With that, it's a virtual click, Michael. So who are we? Let me first introduce Michael. So he's a principal member of technical staff at AMD. So he is working really on compilers for the CPUs and GPUs, in particular the FORTRAN compiler. And he's working in HPC since 2003. So I know him since more or less that time, have experienced him in various roles. But most importantly, in this context here, he is a member of the OpenMP Language Committee since 2009, and he's responsible for some of those features. Yeah, so he knows the background here. And as I said before, he's the CEO of this ARB, owning the standard since April. I was about to say mid 2016.
All right, and Christian. So Christian works at RWTH Aachen University, and he's a senior research scientist there and actually leading the HPC group. He's doing quite a bit on parallel programming and performance work there. This is also where we got in touch initially as part of our technical career. I actually met you, I think, in Dresden for the first time in 2009 when I joined the language committee. So you're slightly older than me in that organization. And since a very good while, he's the co-chair of the affinity subcommittee. So they take care of all questions around how to bring data and computation closer together for improved performance. And then sort of a little bit of, let's say, advertising. He's the co-author of the book Using OpenMP, The Next Step, which is being published by MIT Press. It's a really good book. I've read it front to back, and I really enjoyed reading it. So it really brings you closer to what OpenMP is and how you can use it in practice. And so it's worth browsing your favorite bookstore and clicking buy for that book. All right, back to you, Christian.
No, actually, back to you, Michael, because you are
Oh,
going
yes,
to
the
talk about the
development
development.
process. Yes. All right. Okay. So the OpenMP Architecture Review Board, that's the governing body that basically owns OpenMP as a specification, as a trademark, and maintains the OpenMP Language Committee, who is driving the development of the OpenMP language itself, so meaning the industry standard and the specification document. And what we try to do in the OpenMP ARB is to give you a directive-based programming model, OpenMP, the OpenMP API, that gives you high-level access to parallelism. And what I mean by that, I'll touch on briefly. But we try to aim for the 3 Ps, right? We want to be performance, so you can squeeze out all performance out of the system that you can obtain using your particular algorithm. We want you to be productive, so you don't have to be necessarily concerned with all sorts of code transformation, boilerplate code generation, and whatnot to make things go in parallel. And we aim to be portable, so that means moving from implementation from machine to machine. You can rely on OpenMP giving you the same semantics, and in many cases, it also has been shown that to some extent OpenMP can be performance portable so that you get decent performance moving along between the systems that you target with your application. The other thing that I would like to make clear is that the OpenMP ARB does not necessarily do bleeding edge research, right? We basically look at what people are doing and what is kind of the common approach in the industry or in the HPC community. And we try to standardize that to simplify a developer's life and make them more productive in writing their code and become more portable, productive, and hopefully also performant. And on the slide, you also see like a logo shot of all the members that we have. And it's a good mix between top-notch users who are really interested in using OpenMP for their supercomputers, but we also have all vendors on board who are developing OpenMP implementations and are supplying the processors and GPUs for your systems, so that we know that there's a tight collaboration between the OpenMP community, the users, and the vendors providing the OpenMP implementations as part of the compiler work they're doing. Then as for the roadmap, so the usual cadence for OpenMP is a 5-year cadence for major releases. We slightly hit the mark, missed the mark with OpenMP 6 because that one took 6 years. I'll get to that in a second. So every 5 years, we're going to put out a new major release. And just last supercomputing in November 24, we released OpenMP 6.0 the week before the show took place. So that is the current specification document. And that is what we're going to talk about as part of this 2 webinars series of OpenMP updates. Then I already said that we slightly missed the mark for OpenMP 6. We had another 5.2 release that we put in before 6.0. That was a cleanup release that we did to clean up the OpenMP language and just straighten out a bunch of historic baggage that we accumulated over the past 25 years. And so that was one of the reasons why we had this additional year that it took to bring out OpenMP 6 to the market. So with a 5-year cadence, the current plan is that in November 29, so it's still a bit to go, but as we all know, time flies. So there will be OpenMP 7 in November 29, likely again the week before supercomputing in that year, wherever it may be. And in between, we are planning for an OpenMP 6.x release. It's unclear at this point if it's going to be 6.1 or 6.5. Depends a bit on what we're going to do in the next 2 years, but that one is planned for 2026. And in between, there's going to be what we call a technical report. So every year, again, in November, the week before supercomputing, we put out the technical report in years where we don't do a release, just to give like a progress report on what we're doing in the language committee and where we are in terms of specification work, so that ideally the community can give us early feedback on the direction that we're taking for the next minor or major release coming up. All right, and then I said something about productivity. So this is my one of my favorite slides about explaining how we think about OpenMP. So there's a spectrum between descriptiveness, where you express the what, so your intent, your desire, your parallelism that you want, and you pretty much ignore how it's implemented on the system, and you rely on the quality of your implementation to basically figure out how to implement your intent on the underlying execution environment. On the other end of the spectrum, there's prescriptiveness, where you actually express the how. So you actually have a say over how things are done. You focus on the implementation, and you can influence the compiler, the runtime system, and the whole software stack towards a certain implementation mechanism that you want, and you can control, expose more control over the execution that is taking place. And OpenMP really tries to have a good mix across all of the spectrum. And I just put, I just picked like 4 features out of the OpenMP specification and qualitatively put them on the spectrum. So if you just say pragma OM4, that's actually rather prescriptive because you actually don't specify the exact scheduling, you don't specify the number of threads that you want. So there's a whole bunch of knobs that the OpenMP implementation can choose from. And so let's take that as the middle ground for prescriptive versus descriptiveness. And then towards the descriptive nature, we have tasking, for instance. When you read through the OpenMP specification, there's a lot of can-dos or mays in the specification where the implementation may do something when you flag a task. And so that's very descriptive in its nature. And then we actually have a very descriptive loop feature where you basically say, this is a parallel loop, and the implementation is almost free to choose how to implement it. On the prescriptive side of things, you can actually turn the favorite work sharing construct for or do, depending on which base language you use, into something very prescriptive where you can influence the actual scheduling algorithm that is being used, and you can influence the chunk size so that you can achieve an algorithm to, say, cache line mapping in OpenMP if you care about that, that detail. And so we really try to strive this subset and support it and have a path from the very descriptive features to the very prescriptive features in OpenMP so that you can be productive, and where you actually care about performance, you can have control over what's going on. And then the development process. So this is how the sauce is made. In this case, the specification. So we have a strict process. So coming from a proposal, which we usually collect from the community via IWAMP, Stack Overflow, our user base in the OpenMP ARB, we basically come up with a proposal that where we think this would be a useful addition to the OpenMP specification. Then we turn this into an implementation in LaTeX. So that means we actually write the specification text in this description language. And then there's a voting process with a first vote that basically gathers attention, and then a second vote that basically votes the feature into the specification. Then there's a verification process. And once the verification has been done, we merge everything into the mainline branch. And that is current. This is sort of the current draft of the OpenMP specification. And of course, this process is not necessarily linear. So, when a proposal comes up, it's being iterated a bunch of times until we have confidence that this is actually the feature and the semantics that we want in OpenMP. The implementation in LaTeX is also usually an iterative process, sometimes down to the exact word that we use in a sentence. So that also takes a bit of time until we're happy with the specification text. And then verification, of course, can also be a cyclic thing to do, where we have to repeat the process of making sure that everything is all right a few times to make sure that what we merge is actually what we desire. And then at some point shortly before a feature or a technical feature release or technical report release, we run through this release process. So from the current draft, so whatever's at that point in mainline that we call final and feature complete, we create a draft version. Then this draft version goes to Q&A and editing. So that basically means that usually Bronis, the chair of the language committee, plus myself read the whole specification from page 1 to page N. Correcting things, looking at the inconsistencies together also with the technical committee, who get to have a look at subsets of the specs. Then there's some editing involved, like making things look pretty. And for a feature release, we put out a comment draft. That usually gives us some feedback that we use to do corrections, another round of QA and editing. That gives us the final draft that goes to the ARB for final approval. And once the ARB has conducted an affirmative vote, of that draft. It goes to the OpenMP web team for publication, and then the release process starts with X announcement, Blue Skies announcements, Facebook announcement, and whatnot, so that the community is now aware that we have this new thing out there. All right, let me also talk a little bit about base language improvements. So Christian already kind of mentioned it. So one of the major things that we did in OpenMP 6 is we completed support for all three major languages. So we have complete support for C23 and C++23. We completed support for FORTRAN 2018, and we also have complete support for FORTRAN 2023. And the interesting thing here is why FORTRAN shows up twice. So the usual approach when we develop these kind of base language updates is we basically in the spec at some point say we support FORTRAN 2023, except for all the new features it introduces over 2018. That's where we start as a baseline. And then we go through all the base language features and we knock them off the list where either we don't have any OpenMP impact, or we knock off a feature if it has OpenMP impact, if we have updated the corresponding parts of the specification to deal with this update of the base language. And then over time, that list becomes shorter and shorter. And so for 2018 FORTRAN, we didn't fully complete that list before we had 6.0. So we basically knocked off the last items on that list for 6.0. And as part of that process, we also introduced 2023 support. There may still be restrictions. So that doesn't mean that you can use anything out of those base languages and OpenMP will deal with it. So I picked a particular example of my daily work in FORTRAN. So one of the things that we just restricted away in OpenMP because it absolutely makes no sense, you cannot use data sharing clauses with co-arrays. So anything that has a co-index in an array expression or array statement, you cannot use that inside data sharing clauses. So this is a restriction that we put in, and then we checked off co-arrays from the list. Okay, so the other thing that we did in FORTRAN, FORTRAN now has the block construct. So they basically introduced this to cope with syntactic scopes in the language, right? FORTRAN didn't really have this. C++ has curly braces for this. And so whenever you wrote FORTRAN in OpenMP, you had to use omp parallel to start a parallel region, and then omp end parallel to end it. And that was kind of the marker of the code block that you wanted to run in parallel or with other statements. And since OpenMP now has FORTRAN support that or FORTRAN base language support that supports the block construct, you can now also use this kind of syntactic bracket of block and block in FORTRAN to not only indicate to OpenMP what should be the place where or the syntactic scope of the effect of a directive. So in this case, between block and end block, but you can also use it pretty much similar to C++ to also have local variables that are then automatically prioritized. And this is one of the things where we had to specify in OpenMP how OpenMP should behave in the presence of these block constructs. So this is a rather convenient feature. It helps structuring regular FORTRAN code, and if you structure your FORTRAN code that way, you can directly exploit that as part of OpenMP's parallelization features. The other thing that we actually started in OpenMP 5 and completed sort of in OpenMP 6 is C++ attribute syntax. So with C++11 and C with C23, they have introduced the notion of directives or attributes that you can stick into this double square brackets to give the compiler more information about your code. And so the original intent by C++ was to basically go and say, here's like this variable is intentionally unused, or here's a bit of, code that has certain properties. And when you actually look at the C++ proposal for attributes, they actually mention OpenMP as one of the use cases. So basically, we took that as a wish by the C++ community and basically spent a good time of the language committee in fleshing out how you can turn OpenMP directives into directives in this attribute form, so that now you can specify parallel regions not only with pragmas, which sort of feel like out of the 20th century. You can now have a 21st century feature in C++ and make this really look like nice and shiny C++ code. All right. Let me just quickly take the question that is in there. Now the block, end block construct or statements are not just only for parallel construct. They can be applied to anything in OpenMP that requires a syntactic scope. All right, back to you, Christian.
Thank you, Michael. So now we are going to switch topics. I would like to briefly give you an overview about the nice new things that we have with respect to tasking. Next, please, Michael. Okay, so what's new in OpenMP is that it defines the OpenMP threads to be a member of a logical thread pool. Yeah, as always, the OpenMP standard doesn't give you any details on how it has to be implemented. And there was always, I would say, in all relevant implementations, something like a thread pool behind the scenes. But now with OpenMP 6, you can specify that there's a certain thread pool in the context of OpenMP. And you can specify the limit with this OMP underscore thread underscore limit environment variable. What's more relevant, more interesting, and fits into the concept, into this context, is that OpenMP 6 adds the concept of so-called free agent threads. And I have an example on the next slide, but first let me explain what this is about. So there have been several names on that in the past, in blog articles, maybe more interesting or relevant in papers, but also presentations by the language committees. So basically, these are those threads that are not part of the traditional team created by a parallel region. So these hang around somewhere, more on that in a second, and are available to execute tasks. So if you have been using tasks before, in many cases there was a pragma OMP parallel directly followed by a master or single or a masked construct recently. Now this is not necessarily necessary anymore, because we have the so-called threadset clause that you can specify on a task, which then will indicate which set of threads may execute this particular task. There's the OMP underscore team qualifier. That means you get what you're used to in OpenMP. So that means the threads in this team as created by a corresponding parallel region are allowed to execute this task. Or you can ask for OMP pool, which means any thread in this pool. That means any thread in the current team and any unassigned threads in the thread pool, as I said before, are available to execute this task. And with that, it's a click to go to the next slide. So this is an example which we used, a figure that we used in a similar way onto our introductory slides to explain the tasking. So we have an unbounded while loop. That means you can assume this code is iterating over a linked list, and as long as there's a new element found in the list, there's a task being created to do some compute on this element, and then the element pointer is increased. So the typical pattern was to create a pragma OMP parallel single, so that one thread would do the iteration of the while loop and create a task that captures this element pointer named lm in every iteration of this while loop. However, with this new feature in OpenMP, you don't need the parallel single anymore. You don't need the parallel at all anymore. So we have an initial thread. That's a thread created or that comes with your program. No team involved here. And this one is creating tasks which are put into the task pool. And we have the so-called unassigned threads that are available to execute this pool. And as I said before, we have this pool, and there's the OMP underscore threads underscore reserve environment variable, which means we can divide this pool into 4 structured threads. That means to be used by the parallel region, into 3 agent threads that are available as those unassigned threads shown in the picture on the left-hand side of the slide. In my personal opinion, this underlines that tasking is more important. Yeah? So you should consider tasking for more and more use cases because it's a solution not only for those unstructured parallelism, recursive parallelism, but also in many cases to react to load imbalances, being it because of your application or being it because of dynamic behavior in the hardware. Yeah? So this underlines tasking is important for OpenMP. So we continue in this direction on the next slide. Yeah, we have also a new feature, and Michael said that very well earlier on. So OpenMP is not, or the language committee is not necessarily doing the underlying fundamental research on programming models and systems. Maybe some people there do, but not all of them. But OpenMP tries to standardize what is a good practice found out by the overall community. And the task graph construct is, although a very new one of those features that has been shown to really improve the efficiency and also performance of codes, in particular on modern many-core devices or accelerators, for example. So what's the idea here, as shown in the left-hand, or just one sentence? So it enables the OpenMP implementation, meaning the runtime, to create a record of the sequence of tasks and possibly also its dependencies. So what you can see on the left-hand side in this code figure is that there's again a while loop, and as long as tolerance is not reached, there's a certain for loop being executed that creates per loop iteration 2 tasks. The first one is doing some pre-processing. The next one is doing some compute. So the compute task obviously depends on the pre-processing task. So these have to be executed in order. But on the same side, it's important to create fast enough of these tasks to get all the processing elements busy, meaning the cores or whatever is executing this code. But still, if you would, if you know the task graph, there are better or worse execution orders of this whole set of tasks that's being generated. Of course, dependencies are always fulfilled because it's a requirement for correctness. But if the pre-processed task, just for an example, created this AJ, being an element, maybe even something larger to sit in a cache, it would be good to execute the compute tasks as long as this data is still in the cache, to just give you an idea of how performance could be improved by knowing this task graph. And then there are a couple of tunables I'm not going to detail that allow you to adjust this behavior. In particular, you can ask the runtime, or you can instruct the runtime to discard all existing knowledge about task sequences of execution in case you as a programmer know that from now on the pattern and behavior changes. There's more on the next slide. Let me talk about task iteration. That's a helper construct, or helper clause, sorry, to some extent, that allows us to apply other features like dependencies as shown in this example, or affinity as not shown in this example, in the context of a task loop construct. So let's remember the task loop construct decomposes a certain loop, as shown in the code here twice, into a set of tasks, either one task per iteration, or one grouping multiple tasks together with a grain size, or leaving it up to the implementation, or setting the number of tasks in total, and so forth. So there are a couple of options. However, when using the task loop construct so far, features like dependencies or affinity were not available. So the task iteration allows you as a programmer to specify, well, the task iteration. Yeah, I don't have a better description for that, maybe at the start of the loop body in these particular examples, and then specify the dependencies in, yeah, to some extent, an abstract pattern. So that means these will be applied to the tasks that are being generated by this task loop. That means in the decomposition of the corresponding loop. And that allows us, yeah, or allows you as a programmer to specify dependencies and also affinity between tasks within a task loop, outside of a task loop, as standalone tasks, and so forth. Yeah? So it's an extension, or let's say a so far missing incorporation of features that were available without the task loop before. And then there's a final new thing on tasks on the next slide. These are called transparent tasks. Yeah, here I have to admit I have very little experience with this feature, but I've seen some codes, yeah, where we need that. So if you think of task dependencies, yeah, these were so far, meaning to OpenMP up to version 5.2, limited to task siblings. That means tasks generated in the same task or in the context of a task group construct. However, in some cases, yeah, when you're writing, trying to write composable software components, libraries, and so forth, it was not possible to extend the task dependencies among this context of task siblings. And the idea of transparent tasks is to remove this limitation, as shown in the left-hand side. So we have a task T2, that's the second one, that has this transparent clause added to the task construct. And that means, without any additional modifiers, it will import existing dependencies, but also export dependencies that are being expressed during the execution of this task. And you can specify if you want importing and exporting, or only importing or only exporting dependencies with additional, as I said, modifiers that are not shown on the slide. And this importing of dependencies means that T3, within this task, has to wait on T1, because from T1 we have the output dependency. That means in the context of data flow, X is being produced, and in T3 we have an in-out dependency. That means X is being consumed and produced. And if you continue, we have task 4 that now has to wait on T2, on Y, and T3 on because of X, again because the task dependencies of T2 are being exported. So again, this is an as I said, a feature we have seen very little codes that need it, but apparently there are some. So you should consider that feature when writing task parallel components and software. And with that, I give back to Michael.
Yes. All right. And I'm going to talk about loop transformations. So this is not necessarily something that is immediately obvious, because these are purely sequential features. So they don't really parallelize your code. But first of all, one thing that you will find yourself doing if you are an application developer is that you sometimes unroll loops, you implement tiling. And if you did that once in your life, you probably know that it can be rather cumbersome, even in the most easiest loop transformations, to get them right and not introduce any additional bugs on top of your algorithm. But why did we specify them in OpenMP? Well, in the future, they will be part of the parallelization feature. So in the future, you will be able to express things like, take this loop, tile it, and then run it in parallel on my machine. So this is kind of laying the foundation for a bigger thing to come in the next couple of OpenMP releases. And we implemented a whole bag of those. Some are dramatically useful. Some are like, yeah, it's good to have them because some applications may need them. And I'm going to go through a few of them in the next couple of minutes. So the first one is loop unrolling. So this is, if you're an HPC programmer, this is a standard tuning practice to reduce loop overhead and increase potential for pipelining. So, I'm going to show the rough transformation in a very simplistic way. The reason for this is that the real estate on a slide is rather small, at least if you want to still read it. So basically, think of call body being something really, really big and fancy, or at least something more than a simple call statement. And if you do this yourself, this is a loop running for iterations from 1 to 4. You can reformulate that into a subroutine that calls the body, and then each invocation of that body basically is the original loop index plus 0, 1, 2, and 3, right? So this probably you've done before to increase the potential for software pipelining or whatnot on previous architectures. And with OpenMP 6, actually OpenMP 5.2, you can already, ask the compiler to do this as part of the usual transformations that the compiler knows anyways. And now you have a way to tell the compiler and explicitly request this kind of loop unrolling. So in this case, I'm using unroll full, which basically means completely unroll the loop, right? So obviously that needs a compile time constant for the upper bound or even for the lower bound. So in this case, it's running from 1 to 4. So I can tell the compiler completely unroll the loop and basically do what I'm showing on the left-hand side, just write down the loop body like 4 times and make sure that, the index is set properly. And so that also effectively means that if you completely unroll a loop, the loop is actually no longer present because you just wrote the code enough times to cover the loop that you had before. So this is kind of the easiest transformation that we have. The next level of complexity is that when we introduce a dynamic upper bound, in this case, the standard tuning trick is you add an increment expression to the loop. So in this case, we are incrementing from 1 to n in a step width of 4, and then we replicate the loop body like 4 times. And you may already kind of sense that this is not correct, because down here at the end of the loop, I would actually have to have sort of a remainder handling in case if n is not a multiple of 4. And I'm skipping that, right? It just makes things more complicated. And so, and that's where things become a little crazy for if you want to do this yourself as a manual code transformation. In OpenMP, the compiler takes care of this. So basically you can say, unroll this loop partially, right? And I want the unrolling factor to be 4. And then the compiler takes care of, making sure that the loop is properly unrolled and that a proper remainder handling and ideally also an efficient remainder handling is being established. And so, if you have partial F, the loop is unrolled with F as the unroll factor. So the upper bound and the lower bounds can now be a runtime value. And the compiler will make sure that the safety checks are in place so that your code is actually running through all the iterations, regardless of the actual number of iterations being done. Okay, the next one is tiling. So that is particularly useful if you want to optimize a loopness for cache hierarchies, and if you want to exploit something like temporal and spatial locality, which is also the reason why exploiting the cache hierarchy then actually works. And so in OpenMP, what you can write is tile, and then through a clause, you can specify the size of the tiles that you want in each dimension. And then, this is where things become really convenient with OpenMP, because now it's easy for you to adjust the tile size by, putting in either configuration options as part of the directive. So, and the compiler will do this automatically at compile time. And if you have deeper loop nests, like not only a 2-dimensional loop, but a 3-dimensional loop, you can actually pick, how many loops you want to tile and how many you want to run without tiling being applied. And so when you apply this, the rough equivalent, again, skipping remainder handling, is done like this. So the compiler introduces 2 outer loops that enumerate the tiles, and then the 2 original inner loops are then being used to iterate within each of the tiles. And of course, this code again is not correct because it doesn't have the remainder handling. So you have to have handling of partial tiles, and to make this really efficient, that becomes rather cumbersome if you do this manually. So this is like a safety net also for the program, because usually the compiler does that correctly. Okay, and so the outcome then is, if you have this loop iteration space, in this case, it's a 2x2 tiling, and then you can see how the code would iterate in those tiles across the individual tiles and iterations. One thing I wanted to talk about is the difference between tiling and chunking. So you can think of tiling as multidimensional chunking. So here, I'm showing a piece of code that uses schedule static comma 3 and a collapse of 2. So basically, we take the 2 loops, we collapse them into a single product loop that then runs from 1 to n times m, right? And when we apply static scheduling to it, the loop schedule roughly looks like, come on, there should be an animation there. Nope. Oh, it's showing it. Okay, good. Sorry about that. So you can see that it's package of 3. And then at the end of the iteration space, we basically wrap over to the next layer of the J loop, and then we keep packing loop iterations of 3. In the multidimensional chunking with tile sizes, you can actually see that we get these 2-dimensional tiles, 3 by 3 in this case, and then we get those partial tiles at the boundaries of the iteration space. All right. Loop interchange, that's another good one. So this is also very useful, especially in cases where the data access pattern in your code doesn't necessarily fit the loop iteration space pattern. And so one way how you could think about this is to basically rearrange the loops so that they actually match the pattern. And loop interchange is the OpenMP way of doing this by giving it the permutation clause. You can say, what is the new outer loop, what is the new middle loop, and what is the new inner loop if you have this exemplary three-dimensional loop nest. And so when you specify it like this, the K loop becomes the outer loop, the I loop moves down 1 level, and the J loop also moves down 1 level, so that you now have a KIJ loop, which obviously better matches the layout of the loop indices in my mock-up loop body. We also have loop reversal. So here the idea is, you write your loop in either direction, forward or backward, and then omp reverse basically turns the loop around. So in this case, it's running backwards. If you had a backward loop written down, it would run forward. And again, this kind of adjustment of the index is kind of the difficult part in at least larger loops. To get this right, you have to invest a bit of your time. And so the compiler here really helps you to get this, to do this in a very consistent and hopefully error-free way. And then almost finally, there's loop fusion. So if you have 2 loops that have very similar loop bodies, so in this case, running from 1 to n, you can actually cram those loops into one single loop using loop fusion, so that you again have less loop overhead, and you can basically run through the loop and in some cases also exploit cache locality and or temporal and spatial locality in your loops. All right, and then the final one, loop index splitting. So here, you have a loop iteration space, and what you want to do is you want to actually cut it into two loops. So it's kind of the reverse operation sort of loop fusion. You split a loop into two, but you don't do it like according to the body. You do it per iterations. So basically, in this case, the first k iterations are moved into a separate loop, and then the remaining loop iterations from k to n are then running in a separate loop. And this can be very useful in cases where you want to peel off iterations, for instance, for SIMD or memory alignment. So that this loop pretty much runs unaligned, and then this loop runs in an aligned fashion, and then gives you better performance. The other loop transformations that I was showing, fusion, again, it can reduce the loop overhead and get more work done per loop iteration. And then reversal, it can create forward memory references. And then there are some corner cases where you have your first loop running forward, and then a dependent loop after that you can run backwards, so that the end of the first loop is still hot in the cache and can be picked up by the second loop, and you get slightly better cache locality doing that without actually rewriting your code. You can just stick in the corresponding OpenMP directive. Now, this becomes effectively more useful when you compose these things, right? So you can compose them as you wish, right? So you can, in this case, what I'm going to show is we can use tiling. So we're going to tile the I and J loop into 2x2 tiles. And then we completely unroll the inner loop so that they're completely gone from the resulting code on the machine. And so in this case, the way this works is the tile construct basically gives the compiler the information how large the tiles should be, including partial tile handling. And then OpenMP has this apply clause that all of the loop transformations understand. So basically the outcome of this is, a loop that has an intertile loop that I was showing on my previous slides, and that has intra-tile loops, so the loops that are running inside the tile. And so what I'm specifying here is, after tiling has been applied, apply to the resulting intra-tile loops, so the loops inside the tile, full unrolling, which we can do because we have a fixed loop upper bound, so we know how many iterations we're going to run, and we apply that to both levels, so that both dimensions of the inner loop or the two inner loops are completely unrolled, and the resulting code roughly looks like this. So the I and J loop, they iterate across the individual tiles, and then the inner loop within a tile are completely unrolled. And once you do this, it becomes dramatically easier to exploit cache hierarchies, to optimize loops for SIMD execution. And in the future, like I said, we will be able to also parallelize over those tile loops, so that you can use the tile loops as the input to your work sharing constructs, and parallelize over those loops. And also rearrange them so that they directly match the requirements and needs of your underlying hardware. Christian, you're up.
Yes. And this is now the final feature. Just a click, Michael. The final feature that we're going to explain and present in this webinar. And I created 2 slides because I wanted to remind you that we have inductions, and then I will talk about, very briefly, user-defined inductions. So I think all of you know what a reduction is. Yeah? In an introductory tutorial, I would say it privatizes a certain variable, computes partial results, and then combines those partial results. I mean, the computation of partial results is done with this private variable, and then finally combines those partial results in a synchronized operation applying the reduction operator. So what's an induction? Yeah, so it allows the parallelization despite the presence of some dependencies. Yeah, so to help you a little bit to understand that, let's assume we have, or typically We have an iterative computation, yeah, for an induction to be applied. That means the result is calculated through the repeated application of an operation. Yeah, if you take a look down there, we have xi equals xi times x, yeah, repeated application of an operation. We have a parallel accumulation, so that means these operations can at least partially be done in parallel, yeah, similar to a reduction. That means we have partial results that are being combined into a final result. However, partially means, yeah, in contrast to the reduction, the initialization is not clear, yeah, or it's not, maybe not obvious, or the compiler can't do it in the runtime without your help. Yeah, I hope that's a better explanation. So in a reduction, the initialization of the private variables is done with a neutral element. Here we need something, yeah, so that we have an inductive process, so that the for a thread that does not start with I equals 0 in this particular case, it has a way to compute a partial, the initialization of a partial result, which is not the neutral element. Yeah? So I hope that makes clear what the difference is. And so here, yeah, we have a reduction on the result, that's C of I times xi. Yeah, so computation of, I'm missing the word, polynomial. I hope that's the right term here, right? And x of I equals x of I times x is what we have to do in every iteration here. So we have an induction, the step variable is x, yeah, and the multiplication is a induction operation. That was introduced with OpenMP version 5.x. Yeah, I forgot, I have to admit, but OpenMP 6 introduces user-defined inductions, which I have on the next slide. And that allows us, or you as a programmer, to have even more complex computations in the presence of dependencies. So in the middle of this code block, you have the OMP declare induction, yeah, to some extent similar to the OpenMP declare reduction for user-defined reductions. So my example works on a struct that's called component, which has two components, A and B. And we have an addition operation that adds the argument st, standing for the step, to the corresponding components of an argument. So that induction that is being declared contains a name, which is the OP here. It has a certain result type, which is a component. It has the step type, which is an integer here, st, and it has the actual induction operation, or the inductor, which is a call to the add function. Yeah, that's your function, takes an OMP out and the OMP step, very similar to the placeholders in the user-defined reductions. And optionally, it has a collector. I'm sorry, that specifies this closed form function, as I said before, to enable the starting and arbitrary iteration. So the ice x, I hope that translates, yeah, is the 0th x plus s time I for a given step s. Yeah? So what's special in this example, different from a reduction, is that the amount that's added to the struct's members is multiplied by I, yeah, by the index, and it's not a constant addition. And what's not in the example, but what's important to note and understand, is that user-defined inductions can be used with the parallel for, as shown here, work sharing construct, but also with SIMD loops. And yeah, this enables again the applicability of these constructs to some more codes. And looking at the time, yeah, I think we can close the presentation of features. And with that, thanks for your attention so far. But don't run away. Yeah, there have been a few things in the chat. We are happy to answer your questions.
All right. Yeah, there have been quite a few on the loop transformation stuff. So I'm gonna read them out and directly answer them. So not ignoring you, Christian. I'm gonna leave the hard C++ question for you anyways. Okay. Can this loop tile or loop unrolling be used in a no OpenMP context? So that means outside of threads tasks, similar to like OpenMP SIMD. Yes, exactly. You can use that even if you don't use any parallel regions. You can fire up these directives in your OpenMP compiler and even use that on your sequential code. And potentially some implementations similar to what they did with OpenMP SIMD will have a way to say only enable SIMD, and with loop transformations in the future, they may have a switch like only enable OpenMP loop transformations without everything else outside of those constructs in OpenMP. So you don't get parallelism at all. You just get the loop construct. So that's one thing. The second one is, can the loop transformations be combined with the OpenMP loop or parallel for constructs? Yes, in the future. We're still working on those, but the idea is that once you have the transformed loopness, that you can then apply parallelization features on top of them, and even move the parallelization in the loopness around. So we are still working on getting that done. Not sure if it's going to hit 6.x. Maybe 7, we will see, but we have this on the roadmap. And then, can you have runtime tiling dimensions? Yes, you can. So in the slides, I used compile time constants, but actually these are arbitrary integer expressions. So you can even have that as an input. So you can have, like you mentioned in the chat, sizes of n, n. And so you can easily make that a runtime tunable to be flexible in terms of cache size. All right, and then Christian, that one is for you.
Yeah,
Is
so
the C++ attribute syntax with OpenMP simply an alternative way of specifying OpenMP pragmas, or do they have additional advantages and features?
yeah, so that's a fair question. So I believe, yeah, the main motivation for supporting OpenMP and C++ attributes is first, yeah, to support this aspect of the base language, and second, to react to criticism from users that pragmas are kind of outside of the language. And this is to some extent correct, to some others is, yeah, that's at least a question or a topic for debate. So a pragma, of course, is a compiler directive. It's not really part of the language. Some tools break, yeah, when there's a pragma, although this has been addressed in the modern C++ toolchain in previous years. I would say it's not something to really criticize. However, yeah, users have been asking for it. Programmers have been asking to introduce OpenMP with attributes. This has been done. Now this is really making part of a language feature, yeah, that has been designed with something like OpenMP in mind. So I think it's important to have it there. That was to some extent a personal opinion. I think that's fair to add as a disclaimer. So at the end of the day, is it an alternative way, or does it have additional advantages? I believe at the current point in time, there's no additional advantage or feature than just the personal preference of style. I would even add that a couple of pragmas are not directly available in attributes, or that a few things are probably strange to express, yeah, but that might be my limited experience with using attributes. At the moment, I can't prove that all pragma features are available as attributes. However, in the future, this could change. Yeah, as I said, with the tooling in C++ changing, yeah, adding support for attributes. This could improve the applicability of OpenMP in C++ 23 and later versions. Yeah, but I can't give you a convincing vision at this point in time. Yeah, so short summary at the moment is this is personally a personal preference, probably a personal preference. That's what I wanted to say.
Yeah, thank you. So we don't have any more questions in the chat, but does someone else have a question? You just, start speaking or just raise your hand. Okay, that doesn't seem the case. So thank you very much for the speakers to give us this introduction in OpenMP 6.0. As I mentioned in the beginning, so this is part 1, covering host side features, basically things which relate to the CPU usage of OpenMP. There's a second part which is scheduled for February 18, 2025, where Christian and Michael will tell about the accelerator part of OpenMP 6.0. Watch out the POP website and the POP social media channel mid-January for registration for this second part of this webinar. And with that, thanks everyone for joining. I hope it was interesting. At that time, I also can say like happy holidays. I hope everyone gets some rest, and Happy New Year, and see you next year in some future POP webinar. Thank you.
It was a pleasure. Thank you.
Thank you.